we have a truck with a weight or a box in the back, level bed, and I know it's not a very good looking truck, but we have to take what we can get. Okay, so we have a box 2.5 meters from the cab of the truck, so we don't want the box to slam too hard into the cab of the truck when we hit the brakes, and that's the essence of the problem here. So we have the information that the coefficient of static friction is 0.3. Actually, the way it's stated in the problem is that friction can exert a force up to 30% of the weight of the box. So the frictional force is less than or equal to 0.3 times the weight of the box. But you understand that that really just says the coefficient of static friction is 0.3. Okay, now this is static friction, okay? So we should probably note that. I said it, I just didn't note it here. So for the static case, this is what we have. For the kinetic case, if the box actually starts moving, then we're into kinetic friction, and the force is going to be 25% of the weight of the box. And we've got force of friction here again. We call this force of friction up here. Just to be really complete, I'm going to put K's on these and S here. So this is a force of friction static, force of friction kinetic. And the force of friction kinetic in any case it's not less or equal to, it is 25% of the weight, 0.25 times the weight. Meaning, of course, the coefficient of friction is 0.25. Okay. So, in this case, if the truck hits its brakes and the box actually starts sliding, the net force is just going to be the frictional force. It's the only force acting in this direction. And of course, the downward force is balanced by the upward normal force of the bed on the box. So the only force is the frictional force, which is 25% of the weight of the box. Now, to be sure that the box really does slide, okay, the acceleration of the truck is said to be negative 3.5 meters per second squared, meaning the truck is going to slow down at 3.5 meters per second squared. And that means implicitly we assume that this is the positive direction and that the truck is moving in the positive direction. Now, I should have a calculation here somewhere. I don't see it. Hang on a minute. If the box is stationary with respect to the bed, then its acceleration has to be negative 3.5 meters per second squared. But since the force of friction can apply a force at most 0.3 times the weight, the net force on it can be at most 3/10 of its weight, so that acceleration has to be less or equal to the frictional force divided by mass, or the net force divided by mass, same thing, which is 0.3 times the weight divided by the mass. This implies the acceleration is going to be less than 0.3 g. Why? Because weight divided by mass is g. Weight is the force exerted by gravity. If you multiply the mass by 9.8 meters per second squared, you get the weight. So when you divide the weight by the mass, you get the acceleration of gravity. Okay, so acceleration has to be less or equal to 0.3 g, which is about 3 meters per second squared. Again, if the box is stationary, it needs an acceleration of 3.5 meters per second squared. If it's stationary with respect to the bed, its acceleration is going to be negative 3.5 meters per second squared. That exceeds the maximum magnitude of acceleration that we can achieve from the friction. Okay, so we conclude that the box does move, so that the net force is 0.25 times its weight, which means that if we divide the net force, which is 0.25 times the weight, by the mass, again, we're going to have weight over mass, which is the acceleration of gravity. The acceleration is going to be 0.25 g, 0.25 times the acceleration of gravity, or 2.5 meters per second squared. Now, this is the magnitude of the acceleration. If I put an arrow over it, I have to specify direction, and the direction, of course, would be in the negative. Would be negative, because the frictional force is going to tend to oppose motion, and the motion is going to be in this direction if the box moves. So the frictional force has to be back this way. The acceleration then would be negative 2.5 meters per second squared. The acceleration of the truck is negative 3.5 meters per second squared. It follows, and we'll see why in a minute, that the acceleration of the box relative to the truck is just the difference here, the 1 meter per second squared. So the box, if observed from the frame of the truck, is going to accelerate forward at 1 meter per second squared. From this, you can easily determine how far or how long it would take to travel the 2.5 meters, and also what its velocity would be at that position. Now, there's another way to set this up, which is in terms of the equations of motion for the box and for this part of the bed of the truck, for the back of the cab, let's say, for the end of the bed. In order to see how that works out, first you can see that I've just written this in. We start the clock when the brakes are engaged. I considered this to be implicit when I wrote down these equations. We start the clock when the brakes are engaged, so that x naught of the box is the position of the box at that instant. V naught is the velocity of the truck at that instant. And of course, t is the time as measured from the instant when the brakes were engaged, the instant when the clock is started. So that's the equation of motion for the box. And of course, we've determined the acceleration of the box is going to be negative 2.5 meters per second squared. So we could fill that in. We don't know what the initial velocity is, and as you'll see in a moment, it makes no difference. And we don't know what x naught of the box is. We could measure position from any point we want, so we could let x naught of the box equal 0 if we want, but it's not necessary. Now, the back of the cab, I say x cab, that's what I mean by where the cab starts, the end of the bed, the point of the cab that the box is going to hit. Okay, then the initial position of that point of the cab is 2.5 meters greater than the initial position of the box. The initial velocity of the cab, the initial velocity of the box are identical because the box is riding in the back of the truck without slipping. The acceleration of the truck is your negative 3.5 meters per second squared. Now we can combine these equations, give that a little bit of thought. I'm going to write a couple of things in here. How can you use these equations then to determine the time at which the box is going to hit the end of the truck, or hit the end of the bed, hit the cab? Well, we want to find the time when the position of the cab is equal to the position of the box, because that's when the box is going to first strike, the time when the two first have the same position. Immediately after that, the acceleration of the box is going to change, and we no longer have the uniform acceleration, and these equations no longer apply. But we're not interested in what happens after that. We're just interested in how long it takes the box to get to the end of the bed. So we set the position of the cab equal to the position of the box. Again, the back of the cab. Okay, well, if we set these equal, then we have all this equal to all this. Well, let's subtract all this from both sides. Now, I haven't done that, but say we set equal ... and we subtract the position of the box, the expression for the position of the box, from the position of the cab, and that's going to equal 0. When we subtract, the 2.5 meters will remain, but the initial position of the box will subtract out. The V naught t will subtract out, and so as I mentioned, the initial velocity makes no difference as long as the initial velocity was high enough that the box has time to get to the bed, end of the bed, before the truck comes to rest. And if not, then we have a different problem. Could be an interesting problem, but we're not going to deal with it right now. And then we have half the acceleration of the truck times t squared minus half the acceleration of the box times t squared. And right here it is. Well, we solved that, and that's very easy to solve. I'll write down one more thing just for your reference, but I'll discuss it very briefly. Now, I will let you think through the rest of this, but when we combine this, I can factor out the 1/2 t squared from the acceleration truck minus the acceleration of the box, and I get this. So 1/2 a truck minus a box t squared equals, subtracting 2.5 meters from both sides, negative 2.5 meters. I'll just observe that the magnitude of this acceleration is 1 meter per second squared. So we're actually setting 1/2 times 1 meter per second squared times t squared equal to 2.5 meters. Again, you can work out the details of that, but this justifies our conjecture here that we could just use the relative accelerations to get the acceleration of the box relative to the truck, and validates this interpretation.